Section 3 of The Advance of Science in the Last Half-Century by T.H. Huxley, 1889. I have pointed out that the growth of clear and definite views respecting the constitution of matter has led to the conclusion that, so far as natural agencies are concerned, it is ingenerable and indestructible. In so far as matter may be conceived to exist in a purely passive state, it is imaginably older than motion. But as it must be assumed to be susceptible of motion, a particle of bare matter at rest must be endowed with the potentiality of motion. Such a particle, however, by the supposition can have no energy, for there is no cause why it should move. Suppose now that it receives an impulse. It will begin to move with a velocity inversely proportional to its mass, on the one hand, and directly proportional to the strength of the impulse, on the other, and will possess kinetic energy, in virtue of which it will not only continue to move forever if unimpeded, but if it impinges on another such particle, it will impart more or less of its motion to the latter. Let it be conceived that the particle acquires a tendency to move, and that nevertheless it does not move. It is then in a condition totally different from that in which it was at first. A cause, competent to produce motion, is operating upon it, but, for some reason or other, is unable to give rise to motion. If the obstacle is removed, the energy which was there, but could not manifest itself, at once gives rise to motion. While the restraint lasts, the energy of the particle is merely potential, and the case supposed illustrates what is meant by potential energy. In this contrast of the potential with the actual, modern physics is turning to account the most familiar of Aristotelian distinctions, that between dunamis and energia. That kinetic energy appears to be imparted by impact is a fact of daily and hourly experience. We see bodies set in motion by bodies already in motion, which seem to come in contact with them. It is a truth which could have been learned by nothing but experience, and which cannot be explained, but must be taken as an ultimate fact, about which, explicable or inexplicable, there can be no doubt. Strictly speaking, we have no direct apprehension of any other cause of motion. But experience furnishes innumerable examples of the production of kinetic energy in a body previously at rest, when no impact is discernible as the cause of that energy. In all such cases, the presence of a second body is a necessary condition, and the amount of kinetic energy which its presence enables the first to gain is strictly dependent on the relative positions of the two. Hence the phrase energy of position, which is frequently used as equivalent to potential energy. If a stone is picked up and held, say, 6 feet above the ground, it has potential energy, because, if let go, it will immediately begin to move towards the earth, and this energy may be said to be energy of position, because it depends upon the relative position of the earth and the stone. The stone is solicited to move, but cannot, so long as the muscular strength of the holder prevents the solicitation from taking effect. The stone, therefore, has potential energy, which becomes kinetic if it is let go, and the amount of that kinetic energy which will be developed before it strikes the earth depends on its position, on the fact that it is, say, 6 feet off the earth, neither more nor less. Moreover, it can be proved that the raiser of the stone had to exert as much energy in order to place it in its position as it will develop in falling. Hence the energy which was exerted and apparently exhausted in raising the stone is potentially in the stone, in its raised position, and will manifest itself when the stone is set free. Thus, the energy withdrawn from the general stock to raise the stone is returned when it falls, and there is no change in the total amount. Energy, as a whole, is conserved. Taking this as a very broad and general statement of the essential facts of the case, the raising of the stone is intelligible enough as a case of the communication of motion from one body to another. But the potential energy of the raised stone is not so easily intelligible. To all appearance, there is nothing either pushing or pulling it towards the earth, or the earth towards it, and yet it is quite certain that the stone tends to move towards the earth, and the earth towards the stone, in the way defined by the law of gravitation. In the currently accepted language of science, the cause of motion, in all such cases as this, when bodies tend to move towards or away from one or another, without any discernible impact of other bodies, is termed a force, which is called attractive in the one case and repulsive in the other. And such attractive or repulsive forces are often spoken of as if they were real things, capable of exerting a pull or a push upon the particles of matter concerned. Thus the potential energy of the stone is commonly said to be due to the force of gravity, which is continually operating upon it. Another illustration may make the case plainer. The bob of a pendulum swings first to one side and then to the other of the center of the arc which it describes. Suppose it to have just reached the summit of its right-hand half-swing. It is said that the attractive forces of the bob for the earth and of the earth for the bob set the former in motion, and as these forces are continually in operation, they confer an accelerated velocity on the bob until, when it reaches the center of its swing, it is, so to speak, fully charged with kinetic energy. If at this moment the whole material universe, except the bob, were abolished, it would move forever in the direction of a tangent to the middle of the arc described. As a matter of fact, it is compelled to travel through its left-hand half-swing, and thus virtually to go uphill. Consequently, the attractive forces of the bob and the earth are now acting against it, and constitute a resistance which the charge of kinetic energy has to overcome. But, as this charge represents the operation of the attractive forces during the passage of the bob through the right-hand half-swing down to the center of the arc, so it must needs be used up by the passage of the bob upwards from the center of the arc to the summit of the left-hand half-swing. Hence, at this point, the bob comes to a momentary rest. The last fraction of kinetic energy is just neutralized by the action of the attractive forces, and the bob has only potential energy equal to that with which it started. So that the sum of the phenomena may be stated thus. At the summit of either half-arc of its swing, the bob has a certain amount of potential energy. As it descends, it gradually exchanges this for kinetic energy, until at the center it possesses an equal amount of kinetic energy. From this point onwards, it gradually loses kinetic energy as it ascends until, at the summit of the other half-arc, it has acquired an exactly similar amount of potential energy. Thus, on the whole transaction, nothing is either lost or gained. The quantity of energy is always the same, but it passes from one form into the other. To all appearance, the phenomena exhibited by the pendulum are not to be accounted for by impact. In fact, it is usually assumed that corresponding phenomena would take place if the earth and the pendulum were situated in an absolute vacuum, and at any conceivable distance from one another. If this be so, it follows that there must be two totally different kinds of causes of motion. The one, impact, a vera causa, of which to all appearance we have constant experience. The other, attractive or repulsive force, a metaphysical entity which is physically inconceivable. Newton expressly repudiated the notion of the existence of attractive forces, in the sense in which that term is ordinarily understood, and he refused to put forward any hypothesis as to the physical cause of the so-called attraction of gravitation. As a general rule, his successors have been content to accept the doctrine of attractive and repulsive forces, without troubling themselves about the philosophical difficulties which it involves. But this has not always been the case, and the attempt of Lesage in the last century to show that the phenomena of attraction and repulsion are susceptible of explanation by his hypothesis of bombardment of ultramundane particles, whether tenable or not, has the great merit of being an attempt to get rid of the dual conception of the causes of motion which has hitherto prevailed. On this hypothesis, the hammering of the ultramundane corpuscles on the bob confers its kinetic energy on the one hand and takes it away on the other, and the state of potential energy means the condition of the bob during the instant at which the energy, conferred by the hammering during the one half-arc, has just been exhausted by the hammering during the other half-arc. It seems safe to look forward to the time when the conception of attractive and repulsive forces, having served its purpose as a useful piece of scientific scaffolding, will be replaced by the deduction of the phenomena known as attraction and repulsion from the general laws of motion. The doctrine of the conservation of energy which I have endeavored to illustrate is thus defined by the late Clerk Maxwell. The total energy of any body or system of bodies is a quantity which can neither be increased nor diminished by any mutual action of such bodies, though it may be transformed into any one of the forms of which energy is susceptible. It follows that energy, like matter, is indestructible and ingenerable in nature. the phenomenal world, so far as it is material, expresses the evolution and involution of energy, its passage from kinetic to the potential condition and back again. Wherever motion of matter takes place, that motion is effected at the expense of part of the total store of energy. Hence, as the phenomena exhibited by living beings, in so far as they are material, are all molar or molecular motions, these are included under the general law. A living body is a machine by which energy is transformed in the same sense as a steam engine is so, and all its movements, molar and molecular, are to be accounted for by the energy which is supplied to it. The phenomena of consciousness which arise, along with certain transformations of energy, cannot be interpolated in the series of these transformations, inasmuch as they are not motions to which the doctrine of the conservation of energy applies. And, for the same reason, they do not necessitate the using up of energy. A sensation has no mass, and cannot be conceived to be susceptible of movement. That a particular molecular motion does give rise to a state of consciousness is experimentally certain, but the how and why of the process are just as inexplicable as in the case of the communication of kinetic energy by impact. When dealing with the doctrine of the ultimate constitution of matter, we found a certain resemblance between the oldest speculations and the newest doctrines of physical philosophers. But there is no such resemblance between the ancient and modern views of motion and its causes, except in so far as the conception of attractive and repulsive forces may be regarded as the modified descendant of the Aristotelian conception of forms. In fact, it is hardly too much to say that the essential and fundamental difference between ancient and modern physical science lies in the ascertainment of the true laws of statics and dynamics in the course of the last 3 centuries, and in the invention of mathematical methods of dealing with all the consequences of these laws. The ultimate aim of modern physical science is the deduction of the phenomena exhibited by material bodies from physical mathematical first principles. Whether the human intellect is strong enough to attain the goal set before it may be a question, but thither will it surely strive. The third great scientific event of our time, the rehabilitation of the doctrine of evolution, is part of the same tendency of increasing knowledge to unify itself, which has led to the doctrine of the conservation of energy. And this tendency, again, is mainly a product of the increasing strength conferred by physical investigation on the belief in the universal validity of that orderly relation of facts, which we express by the so-called laws of nature. The growth of a plant from its seed, of an animal from its egg, the apparent origin of innumerable living things from mud, or from the putrefying remains of former organisms, has furnished the earlier scientific thinkers with abundant analogies suggestive of the conception of a corresponding method of cosmic evolution from a formless chaos to an ordered world which might either continue forever or undergo dissolution into its elements before starting on a new course of evolution. It is therefore no wonder that, from the days of the Ionian school onwards, the view that the universe was the result of such a process should have maintained itself as a leading dogma of philosophy. The emanistic theories which played so great a part in Neoplatonic philosophy and Gnostic theology are forms of evolution. In the 17th century, Descartes propounded a scheme of evolution as an hypothesis of what might have been the mode of origin of the world, while professing to accept the ecclesiastical scheme of creation as an account of that which actually was its manner of coming into existence. In the 18th century, Kant put forth a remarkable speculation as to the origin of the solar system, closely similar to that subsequently adopted by Laplace, and destined to become famous under the title of the nebular hypothesis. The careful observations and the acute reasonings of the Italian geologist of the 17th and 18th centuries, the speculations of Leibniz in the Protegea, and of Buffon in his Théorie de la Terre, the sober and profound reasonings of Hutton in the latter part of the 18th century, all these tended to show that the fabric of the earth itself implied the continuance of processes of natural causation for a period of time as great, in relation to human history, as the distances of the heavenly bodies from us are in relation to terrestrial standards of measurement. The abyss of time began to loom as large as the abyss of space, and this revelation to sight and touch, of a link here and a link there, of a practically infinite chain of natural causes and effects, prepared the way, as perhaps nothing else has done, for the modern form of the ancient theory of evolution. In the beginning of the 18th century, de Maillet made the first serious attempt to apply the doctrine to the living world. In the latter part of it, Erasmus, Darwin, Goethe, Treviranus, and Lamarck took up the work more vigorously and with better qualifications. The question of special creation, or evolution, lay at the bottom of the fierce disputes which broke out in the French Academy between Cuvier and Saint Hilaire, and, for a time, the supporters of biological evolution were silenced, if not answered, by the alliance of the greatest naturalists of the age with their ecclesiastical opponents. Catastrophism, a short-sighted teleology, and a still more short-sighted orthodoxy joined forces to crush evolution. Lyell and Poulet-Scrope, in this country, resumed the work of the Italians and of Hutton, and the former, aided by a marvellous power of clear exposition, placed upon an irrefragable basis the truth that natural causes are competent to account for all events, which can be proved to have occurred in the course of the secular changes which have taken place during the deposition of the stratified rocks. The publication of the Principles of Geology in 1830 constituted an epoch in geological science. But it also constituted an epoch in the modern history of the doctrines of evolution, by raising in the mind of every intelligent reader this question: if natural causation is competent to account for the not living part of our globe, why should it not account for the living part? By keeping this question before the public for some 30 years, Lyell, though the keenest and most formidable of the opponents of the transmutation theory, as it was formulated by Lamarck, was of the greatest possible service in facilitating the reception of the sounder doctrines of later day. And in like fashion, another vehement opponent of the transmutation of species, the elder Agassiz, was doomed to help the cause he hated. Agassiz not only maintained the fact of the progressive advance in organization of the inhabitants of the earth at each successive geological epoch, but he insisted upon the analogy of the steps of this progression with those by which the embryo advances to the adult condition, among the highest forms of each group. In fact, in endeavoring to support these views, he went a good way beyond the limits of any cautious interpretation of the facts then known. Although little acquainted with biological science, Whewell seems to have taken particular pains with that part of his work which deals with the history of geological and biological speculation. In several chapters of his 17th and 18th books, which comprise the history of physiology, of comparative anatomy, and of the paleontological sciences, vividly reproduced the controversies of the early days of the Victorian epoch. But here, as in the case of the doctrine of the conservation of energy, the historian of the inductive sciences has no prophetic insight, not even a suspicion of that which the near future was to bring forth. And those who still repeat the once favorite objection that Darwin's Origin of Species is nothing but a new version of the Philosophie zoologique will find that, so late as 1844, Whewell had not the slightest suspicion of Darwin's main theorem, even as a logical possibility. In fact, the publication of that theorem by Darwin and Wallace in 1859 took all the biological world by surprise. Neither those who were inclined towards the progressive transmutation or development doctrine, as it was then called, nor those who were opposed to it, had the slightest suspicion that the tendency to variation in living beings, which all admitted as a matter of fact, the selective influence of conditions, which no one could deny to be a matter of fact when his attention was drawn to the evidence, and the occurrence of great geological changes, which also was a matter of fact, could be used as the only necessary postulates of a theory of the evolution of plants and animals which, even if not at once competent to explain all the known facts of biological science, could not be shown to be inconsistent with any. So far as biology is concerned, the publication of the Origin of Species, for the first time, put the doctrine of evolution, in its application to living things, upon a sound scientific foundation. It became an instrument of investigation, and in no hands did it prove more brilliantly profitable than in those of Darwin himself. His publications on the effects of domestication in plants and animals, on the influence of cross-fertilization, on flowers as organs for effecting such fertilization, on insectivorous plants, on the motions of plants, pointed out the routes of exploration which have since been followed by hosts of inquirers, to the great profit of science. Darwin found the biological world a more than sufficient field for even his great powers, and left the cosmical part of the doctrine to others. Not much has been added to the nebular hypothesis since the time of Laplace, except that the attempt to show, against that hypothesis, that all nebulae are star clusters, has been met by the spectroscopic proof of the gaseous condition of some of them. Moreover, physicists of the present generation appear now to accept the secular cooling of the earth, which is one of the corollaries of that hypothesis. In fact, attempts have been made, by the help of deductions from the data of physics, to lay down an approximate limit to the number of millions of years which have elapsed since the earth was habitable by living beings. If the conclusions thus reached should stand the test of further investigation, they will undoubtedly be very valuable. But, whether true or false, they can have no influence upon the doctrine of evolution in its application to living organisms. The occurrence of successive forms of life upon our globe is an historical fact, which cannot be disputed, and the relation of these successive forms, as stages of evolution of the same type, is established in various cases. The biologist has no means of determining the time over which the process of evolution has extended, but accepts the computation of the physical geologist and the physicist, whatever that may be. Evolution as a philosophical doctrine applicable to all phenomena, whether physical or mental, whether manifested by material atoms or by men in society, has been dealt with systematically in the synthetic philosophy of Mr. Herbert Spencer. Comment on that great undertaking would not be in place here. I mention it because, so far as I know, it is the first attempt to deal, on scientific principles, with modern scientific facts and speculations. For the philosophic positive of M. Comte, with which Mr. Spencer's system of philosophy is sometimes compared, though it professes a similar object, is unfortunately permeated by a thoroughly unscientific spirit, and its author had no adequate acquaintance with the physical sciences even of his own time. The doctrine of evolution, so far as the present physical cosmos is concerned, postulates the fixity of the rules of operation of the causes of motion in the material universe. If all kinds of matter are modifications of one kind, and if all modes of motion are derived from the same energy, the orderly evolution of physical nature out of one substratum and one energy implies that the rules of action of that energy should be fixed and definite. In the past history of the universe, back to that point, there can be no room for chance or disorder. But it is possible to raise the question whether this universe of simplest matter and definitely operating energy, which forms our hypothetical starting point, may not itself be a product of evolution from a universe of such matter in which the manifestations of energy were not definite, in which, for example, our laws of motion held good for some units and not for others, or for the same units at one time and not at another, and which would therefore be a real Epicurean chance world. For myself, I must confess that I find the air of this region of speculation too rarefied for my constitution, and I am disposed to take refuge in ignoramus et ignorabimus. The execution of my further task, the indication of the most important achievements in the several branches of physical science during the last 50 years, is embarrassed by the abundance of the objects of choice, and by the difficulty which every one, but a specialist in each department, must find in drawing a due distinction between discoveries which strike the imagination by their novelty or by their practical influence, and those unobtrusive but pregnant observations and experiments in which the germs of the great things of the future really lie. Moreover, my limits restrict me to little more than a bare chronicle of the events which I have to notice. In physics and chemistry, the old boundaries of which sciences are rapidly becoming effaced, one can hardly go wrong in ascribing a primary value to the investigations into the relation between the solid, liquid, and gaseous states of matter on the one hand, and degrees of pressure and of heat on the other. Almost all, even the most refractory solids, have been vaporized by the intense heat of the electric arc, and the most refractory gases have been forced to assume the liquid and even the solid forms by the combination of high pressure with intense cold. It has further been shown that there is no discontinuity between these states, that a gas passes into the liquid state through a condition which is neither one nor the other, and that a liquid body becomes solid, or a solid liquid, by the intermediation of a condition in which it is neither truly solid nor truly liquid. Theoretical and experimental investigations have concurred in the establishment of the view that a gas is a body, the particles of which are in incessant rectilinear motion at high velocities, colliding with one another and bounding back when they strike the walls of the containing vessel, and, on this theory, the already ascertained relations of gaseous bodies to heat and pressure have been shown to be deducible from mechanical principles. Immense improvements have been effected in the means of exhausting a given space of its gaseous contents, and experimentation on the phenomena which attend the electric discharge and the action of radiant heat within the extremely rarefied media thus produced has yielded a great number of remarkable results, some of which have been made familiar to the public by the Gieseler tubes and the radiometer. Already these investigations have afforded an unexpected insight into the constitution of matter and its relations with thermal and electric energy, and they open up a vast field for future inquiry into some of the deepest problems of physics. Other important steps in the same direction have been effected by investigations into the absorption of radiant heat proceeding from different sources by solid, fluid, and gaseous bodies. And it is a curious example of the interconnection of the various branches of physical science that some of the results thus obtained have proved of great importance in meteorology. The existence of numerous dark lines, constant in their number and position in the various regions of the solar spectrum, was made out by Fraunhofer in the early part of the present century, but more than 40 years elapsed before their causes were ascertained and their importance recognized. Spectroscopy, which then took its rise, is probably that employment of physical knowledge, already won, as a means of further acquisition, which most impresses the imagination. For it has suddenly and immensely enlarged our power of overcoming the obstacles which almost infinite minuteness on the one hand, and almost infinite distance on the other, have hitherto opposed to the recognition of the presence and the condition of matter. 1/18,000,000th of a grain of sodium in the flame of a spirit lamp may be detected by this instrument, and, at the same time, it gives trustworthy indications of the material constitution not only of the sun, but of the farthest of those fixed stars and nebulae which afford sufficient light to affect the eye or the photographic plate of the inquirer. The mathematical and experimental elucidation of the phenomena of electricity and the study of the relations of this form of energy with chemical and thermal action had made extensive progress before 1837. But the determination of the influence of magnetism on light, the discovery of diamagnetism, of the influence of crystalline structure on magnetism, and the completion of the mathematical theory of electricity all belong to the present epoch. To it also appertain the practical execution and the working out of the results of the great international system of observations on terrestrial magnetism, suggested by Humboldt in 1836, and the invention of instruments of infinite delicacy and precision for the quantitative determination of electrical phenomena. The voltaic battery has received vast improvements, while the invention of magneto-electric engines and of improved means of producing ordinary electricity has provided sources of electrical energy vastly superior to any before extant in power and far more convenient for use. It is perhaps this branch of physical science which may claim the palm for its practical fruits, no less than for the aid which it has furnished to the investigation of other parts of the field of physical science. The idea of the practicability of establishing a communication between distant points, by means of electricity, could hardly fail to have simmered in the minds of ingenious men, since well nigh a century ago experimental proof was given that electric disturbances could be propagated through a wire 12,000 feet long. Various methods of carrying the suggestion into practice had been carried out with some degree of success. But the system of electric telegraphy, which at the present time brings all parts of the civilized world within a few minutes of one another, originated only about the commencement of the epoch under consideration. In its influence on the course of human affairs, this invention takes its place beside that of gunpowder, which tended to abolish the physical inequalities of fighting men, of printing, which tended to destroy the effect of inequalities in wealth among learning men, of steam transport, which has done the like for travelling men. All these gifts of science are aids in the process of levelling up, of removing the ignorant and baneful prejudices of nation against nation, province against province, and class against class, of assuring that social order which is the foundation of progress, which has redeemed Europe from barbarism, and against which one is glad to think that those who in our time are employing themselves in fanning the embers of ancient wrong, in setting class against class, and in trying to tear asunder the existing bonds of unity, are undertaking a futile struggle. The telephone is only second in practical importance to the electric telegraph. Invented, as it were, only the other day, it has already taken its place as an appliance of daily life. 60 years ago, the extraction of metals from their solutions by the electric current was simply a highly interesting scientific fact. At the present day, the galvano-plastic art is a great industry, and, in combination with photography, promises to be of endless service in the arts. Electric lighting is another great gift of science to civilization, the practical effects of which have not yet been fully developed, largely on account of its cost. But those whose memories go back to the tinderbox period and recollect the cost of the first lucifer matches will not despair of the results of the application of science and ingenuity to the cheap production of anything for which there is a large demand. End of Section 3. This has been a Librivox recording. All Librivox recordings are in the public domain.